a set of vectors for which each pair is orthonormal is called an orthonormal set. In particular, if that set is a basis for a vector space, then it is called an orthonormal basis. And so the standard basis for n-dimensional real space is an orthonormal basis. So new definition: the dimension of a vector space V, which we denote dim V, is the number of vectors in a basis for the space So again, considering n-dimensional real space, what we call n-dimensional real space, the standard basis for n-dimensional real space over the set of scalars consisting of real numbers is once again the set B consisting of vectors e sub I, where I ranges from 1 to n. And so the cardinality of the set B, that is the number of elements in the set B, is n. And so this agrees, the definition for the dimension agrees with the way that we've been using the term previously, that is, n-dimensional real space has dimension n. Now recall that the complex numbers are those numbers of the form a plus b times I, where a and b are real numbers and the number I is the square root of -1. The complex plane is a model for the set C as a vector space over the set of scalars consisting of real numbers. So a complex number Z can be expressed, or is expressed in the complex plane, as a ordered pair of real numbers xy, where the number x is the real component of the complex number Z and the number y is the imaginary component of the complex number Z. Now we use the term real and imaginary, but the complex plane once again is a vector space over scalars consisting of real numbers, and so ordered pairs of real numbers. And so the complex plane consists of two axes, both real. A common mistake is to refer to the vertical axis as the imaginary axis. Both axes are real. So a complex number Z is an ordered pair, xy. And in this model, as a vector space, we can add two complex numbers, z1 plus z2 is the sum of ordered pairs, x1, y1 plus x2, y2. And so this is the ordered pair, x1 plus x2 and y1 plus y2. We can also take scalar multiples of a complex number, that scalar being a real number. A times the complex number z1 is the ordered pair a times x1, a times y1. Now, so far, I have only described a vector space as r squared over r. What makes the complex numbers different is that we can multiply them. There is a notion of multiplication of complex numbers. To see this, let's first look at complex numbers in form x sub 1 plus y sub 1 times I, and z sub 2 being the complex number x sub 2 plus y sub 2 times I. Now remember, the number I is the square root of -1, and so I squared is -1. And so when we multiply these two complex numbers, we are multiplying these binomials, x1 plus y1 times I times x2 plus y2 times I. And so if we distribute out, we have x1 times x2 minus y1 times y2. And then we have a multiple of the number I, and that is x1 times y2 plus x2 times y1. And so in the language of vectors, we have that the complex number, which is the product of two complex numbers, is x1 y1 times x2 y2. And this gives us the ordered pair, x1 x2 minus y1 y2. And the second component is x1 times y2 plus x2 times y1. Okay? So considering the set of complex numbers as a vector space over the real numbers, that is, all the scalars are real, a basis for the set of complex numbers is the set B, consisting of the purely real number 1 and the purely imaginary number I, where the number 1 is a vector, and that is the ordered pair 1, 0, and the number I is a vector, and that is the ordered pair 0, 1. So the dimension of the complex numbers as a vector space over the reals is 2. That is, every complex number is a two-dimensional object. So notice that if we multiply the purely real number y in vector form, y0, with the purely imaginary number I in vector form 0, 1, then this gives us the vector 0, y. And so every complex number z, which is an ordered pair xy, can be expressed as the sum of the vector x0 plus the product of the vector y0, again a purely real number y in vector form y0, with the complex number, purely imaginary number rather, I, which in vector form is 0, 1. So again, this is x plus y times I. All right. Now, as we can multiply and add vectors, the set of complex numbers is also a vector space over itself. Since for any four complex numbers, z1 times z2 plus z3 times z4 is once again a complex number for any choice of complex numbers z sub I. And in this light, a complex number is a one-dimensional object, and this is the reason that we can treat it as a pure number. All right, so we'll end here for today. Next time we'll look at complex numbers in much more detail. I hope you have enjoyed the 6th lecture. Thanks for watching.